Hi, welcome to this video. In this video, we are going to teach you the basic knowledge of communication principle. Hope you learn something in this video and please enjoy it. Our group member consists of Lim Chuan, which is me, Gabriel Lumuchun, Chin Chun Yi, and Isaac Koo. And in this video, we are going to learn the amplitude modulation, angle modulation, radio digital modulations, advancements in communication fields, impacts and benefits to the society, and last but not least, misconceptions on the topics in terms of health, safety, legal, or cultural issue.
Have you ever wondered how radio waves are transmitted to the device we use every day? In this part, I'm going to explain one of the most well-known modulation techniques, amplitude modulation, or we call it AM. Just like how it is named with, amplitude modulation is a method in which the amplitude of a carrier signal is various in direct proportional to the waveforms of a modulating signal, which contains the information that we want to transmit. As shown in the figure below, these variations encodes the information that is used to be transmitted, making communication possible. And the advantage of amplitude modulation is because of its ability to transmit modulating signals over a long distance and reduce the impacts of noise and interference. Basically, there are 4 types of amplitude modulation techniques need to be focused on. First is double sideband full carrier, DSBFC. In these techniques, both sidebands and the carrier signals are present in the frequency spectrum after modulation, and the carrier retains its full amplitude, which is simplified demodulation but consumes more power. In order to improve the power efficiency, a second type of technique, double sideband suspensed carrier, DSBSC, has been implemented by improving from the previous technique. It removed the carrier signal, leaving only the upper and lower sideband, which carry the information. And in this frequency spectrum, the carrier is absent, and in the block diagram, the summing junction is removed. This reduces the power usage compared to the DSBFC. Although the SBSC improved the power efficiency, but transmitting both sidebands still use more bandwidth than necessary. By improving the DSBSC, which is adding a filter, the third technique, single sideband SSB, had been implemented by transmitting only one sideband, either upper or lower, making it highly efficient in both power and bandwidth. However, these techniques require more complex equipment for modulations and demodulation. Last but not least, the last technique, vesicle sideband VSB, is a compromise between a DSBFC and SSB. It transmits one sideband and a small portions of the other sideband, known as vesicle. This makes it easier to demodulate than SSB while still saving bandwidth compared to DSBFC. In short, each technique has its own advantage and disadvantage, with the choice depending on the application requirement. All I mentioned just now is about modulation, but to recover back the original signal, we need to perform demodulation, and one common method is by using an envelope detector circuit, which works specifically for DSBFC signal. This method is preferred because it is simple, cost-efficient, and does not require a local carrier signal. The envelope detector circuit typically consists of a diode, a low-pass filter, and a DC component blocker. The diode will allow only the positive half of the signal to pass through, effectively rectifying the waveform, while the low-pass filter, composed of a resistor and a capacitor, it will smooth the rectifier signal to recover the original modulating signal. And to achieve the optimal performance, the RC value must be carefully adjusted. If the RC value is too small, it will cause the signal distortions and excessive ripple, while if the RC value is too large, it results in a slow response, losing signal details. Last but not least, the circuit includes a DC component blockers to remove the unwanted DC offsets for cleaner output. Another type of demodulation method is the synchronous detector or coherent detector. These methods provide better signal quality and recover signals from various modulation types like DSBSC, SSB, and VSB. It uses a local oscillators to generate a carrier signal synchronized with the original carriers used during the modulation. However, synchronizations must be precise, otherwise the distortions may occur and reducing the qualities of the recovered signal.
Let's move on to angle modulation. Angle modulation is also known as exponential modulation, which is a type of analog modulation as well. For angle modulation, the angle of a carrier wave is varied in proportion to the message or so-called the modulating signal, while its amplitude remains constant, which is the opposite of amplitude modulation. The angle can be varied in 2 ways, which are frequency modulation and phase modulation. By understanding what frequency modulation is. Frequency modulation varies the frequency of a signal to convey information. It is used widely over AM due to its immunity to amplitude-based noise and interference. When this frequency is varied instead of the amplitude, it is more resistant to non-linearities in amplification. This means that it can handle distortions when signals are amplified that results in low fidelity. In simple terms, we can say that the data is embedded in high-frequency variations, and we can extract this data at higher frequency part of the FM signal. For instance, let us look at this figure here. As we can see, at the higher frequency part, there is a data embedded in that range, and we can extract the data which is 1 from it. Conversely, the lower frequency range of the signal does not contain any data to extract. In FM, an important concept known as the deviation frequency is used for analyzing the FM signal. This is because the carrier frequency increases or decreases based on the changes of the modulating signal. The deviation frequency is defined as the current distance of the carrier from the nominal frequency of the FM signal. It can deviate in the positive or negative direction with respect to the amplitude of the modulating signal. We will look into it visually later on. But before that, we should know that deviation ratio, or also known as the modulation index of FM, is the ratio of the maximum deviation frequency to the maximum modulating frequency as shown in the formula here. Now, why do we need to know the deviation ratio? It actually depends on different applications. I have listed down 2 applications here, which are music and human speech. For music, they have relatively higher maximum modulating frequency, which in turn needs higher deviation ratio for better audio quality and higher fidelity. Human speech, on the other hand, has lower maximum modulating frequency, so lower deviation ratio can be used just to have enough comprehensible signals. If we were to use lower deviation ratio on music, we might not be able to have enough comprehensive signals to extract them out, leading to low fidelity output of FM signal visually. As mentioned previously, the carrier frequency changes based on the changes of the modulating signal when analyzing FM signals. As the modulating signal moves with respect to time, it increases its frequency until the maximum positive amplitude, and at maximum positive amplitude, the frequency is the highest, which is the maximum deviation above the center frequency. As it moves towards the maximum negative amplitude, it will reach a crossing point first. At this point, the frequency of the modulated signal is equal to the frequency of the carrier signal, which indicates that this is the center frequency where no changes of frequencies are occurring at this point. Then at maximum negative amplitude, the frequency here is the lowest, which is the maximum deviation below the center frequency, and this whole cycle will repeat again as it moves with respect to time. Since we have learned what is deviation ratio or so-called the modulation index, we can categorize FM signals into narrow band FM and wide band FM. For narrowband FM, the deviation ratio is less than or equal to 0.25, and the general expression can be represented as the equation shown here. Now, if you notice something about the equation, EC cos omega CT represents the carrier signal, and the other two terms represent the single pair of positive and negative sideband. Now, if we were to look at this frequency spectrum, the bandwidth of it should be 2 FM, where FM is the modulating frequency. And you can see this actually corresponds to the above equation. To show you how it corresponds to the equation, we will look into the frequency spectrum visually later on. The total transmitted power in FM remains constant and is equal to the carrier signal power. It is distributed among the carrier frequency and its sidebands as shown in the equation here as well. J here is identified from the basal functions of the first kind according to the modulation index. In this case, it is 0.25. We can see that the terms contain J0 and J1, which corresponds to a single amplitude of the carrier signal and one pair of the sideband amplitudes with order of sidebands equals to 1. Let's move on to wideband FM. The deviation ratio for wideband FM is more than 10, and the general expression can be represented as the equation shown here. The number of terms that will be further derived from the equation will depend on the order of sidebands. We should take note that wideband FM have infinite sidebands in theory. Therefore, we will have to use the Carson's rule. Carson's rule is derived for signals with multiple significant sidebands. However, in practice, we can't really take every sideband into account. Therefore, this rule ensures that there are enough sidebands included so that 98% of the signal's power can be transmitted. According to this rule, n is equal to beta plus 1, so the calculation for the bandwidth will be as shown here. The power transmitted in FM have the same concept as narrowband FM. It's just that the order of sidebands is no longer 1 and could be any other order of sidebands.
Spectrum visually. For narrowband FM, only the carrier and a single pair of significant sidebands are present in the spectrum, making it simpler and more efficient in terms of the bandwidth. As bandwidth increases, the fidelity of the signal will be higher, and signals are extracted out in a more detailed way. But the trade-off is that higher bandwidth are not bandwidth efficient, which is why sometimes narrowband FM are useful in different situations, especially emergency. Now, as the bandwidth increases, especially when the deviation ratio is greater than 10, which is the deviation ratio for wideband FM, we can also see that the amplitude of the frequency spectrum is increasing, which is why Carson's rule is applied. In practice, sometimes Carson's rule is even applied even at deviation ratio equals to 5. This is because it provides a practical bandwidth estimation that captures most of the signal's power by focusing on the carrier and the most frequency demodulation. The basic concept to demodulate an FM is to detect the frequency variation in the signal. There are two techniques that we can apply, which is direct method, discriminator plus envelope detector, and the indirect method, phase-lock loop. In short, first method, which is a direct method, discrimination plus envelope detector. Here are the two key stages, which is the frequency discrimination and amplitude demodulation. For the frequency discrimination stage, it converts frequency variation into amplitude variation by using tuned circuits such as LC circuits or other filter. If the frequency variation is higher than FC, it produces a higher output voltage. If the frequency variation is lower than FC, it produces a lower output voltage. And this output voltage produces the amplitude variations as shown in the middle section there. Now for the envelope detection stage, it is also called the amplitude demodulation stage. The signal is no longer an FM but an AM-like signal as shown in the middle stage here. The envelope detector extracts the amplitude of this signal, and here how it works. An envelope detector circuit, as explained earlier in the AM section, follows the peak of the AM signal and smoothens them out to recover the original modulating direct method, which is the phase-lock loop. The process has three main components, which are the phase detector, low-pass filter, and the voltage-controlled oscillator VCO. For the first stage, the phase detector, it compares the phase of the incoming FM signal with the phase of a signal generated by the VCO. It produces an output voltage that represents the difference in phase between the two signals. As the frequency of the FM signal changes, the phase difference changes, and this phase difference is used to track the modulating signal. For the second stage, which is the low-pass filter, it filters out the output of the phase detector to remove high-frequency noise and retain slow varying signal, which corresponds to the original modulating signal. This filtered signal is used to adjust the VCO and is also the recovered modulating signal. Now for the final stage, which is the voltage-controlled oscillator, it generates a signal whose frequency is controlled by the voltage applied to it. The VCO continuously adjusts its frequency to stay locked to the frequency of the incoming FM signal. As the FM signal frequency changes, the control voltage of the VCO changes, which corresponds to the original modulating signal.
Okay, so now I'll talk about phase modulation. So basically the definition of phase modulation is that it's a phase of carrier wave signal that's affected by the amplitude of the baseband signal. So basically carriers phase shift by an amount proportional to amplitude of the baseband signal at any given time. And the amplitude and frequency of the carrier wave signal will always remain the same. So here's the equation of the phase modulation signal, where omega c represents the carrier frequency constant, A represents the amplitude constant, following with phase angle deviation, and Kp is the phase deviation constant in radians per volt. So summarizing all the constants above, you can obtain the formula Vt equals to A cos omega ct plus Kp Vm bracket t. Moving on to radio digital modulation. So radio digital modulation carries the meaning that it encodes the digital information on carrier radio wave for transmission over a wireless communication channel. As you can see from the diagram, modem act as a conversion media that converts digital pulses to a signal suitable for transmission over a communication medium such as radio or telephone. Okay, so now I'll talk about techniques to modulate digital signal. So first of all, we have three techniques, which is amplitude shift key, frequency shift key, and phase shift key. So for amplitude shift key, the radio wave carrier amplitude changes corresponding to highs and lows levels of digital bitstream signal. And while for frequency shift key, radio wave carrier frequency shifts corresponding to highs and low level in signal. More resistant to noise than amplitude shift key, since information is carried by frequency shifts. So there are multiple variants of it, such as binary frequency shift key and multiple level frequency shift key, which gives higher data rate. Last but not least, we have phase shift key, where radio wave carrier shifts in phase corresponding to digital bitstream signal. So there are multiple variants of it, such as binary phase shift key, which shifts 0 and 180 degrees, and quadrature phase shift key. So now I'll explain about multi-level shift key. So multi-level shift key meaning that there are multiple symbols used to represent binary data, allowing more than one bit to be transferred per symbol. Well, so what is symbol? Symbol is actually a unique unit that represents one or more bit of digital data in signal modulation. So for example, binary phase shift key, we have two symbols representing 0 and 180 degrees, and onwards for quadrature phase shift key. So what's the benefit of multi-level shift key? Basically, it transmits more bits per symbol, which increases the data rate without increasing the required bandwidth. So it has higher level modulation schemes that transmit more information in a limited bandwidth, and it can be adapted based on the channel's noise level and interference. It is applicable to amplitude, frequency, and phase shift keying, but multi-level phase shift keying is the most widely used one. Moving on to quadrature amplitude modulation. So quadrature amplitude modulation is a scheme that modulates two sinusoidal carriers 90 degrees out of phase with each other, and there are two components, which is in phase and quadrature. So both modulated carries are summed to result in a signal with amplitude and phase modulation. So phase and amplitude changes can map at many points on a constellation diagram. So these QAM systems can produce 8, 16, 64 until 256 points. So leading to increased number of bits, data bits or symbols that can be transmitted within a limited bandwidth and adjustable quadrature amplitude modulation level based on channel signal to noise ratio. So let's get into, for example, quadrature phase shift key. So for quadrature phase shift key, 4 symbols where each symbol represents 2 bit data, and the phase difference of 90 degrees for 4 different combinations of 2 bits. So it actually carries twice as much information as ordinary phase shift key using the same bandwidth, which makes it much efficient than normal phase shift key. And it can be extended to encode more bits into one symbol, which results into higher order systems such as 8 phase shift key, 16 phase shift key that provides higher data rates.
In this presentation, we'll explore the recent advancements in communication technology, includes their impacts on society, and address some common misconceptions about this. Let's begin by discussing some key advancements in communication technology. The first one is the 5G deployments. 5G represents a significant leap forward in communication standards, offering a higher speed, lower latency, better coverage, and also enhanced capacity compared to the 4G. The ongoing developments include the network expansion, improved coverage, and innovative use cases like the deployment of high-frequency MIM spectrum for even better performance. The second one is the artificial intelligence. The AI has revolutionized communication in several ways. The virtual assistants and also chatbots provide a real-time support, while the AI-driven language translation breaks down the barriers and improves the accessibility. Additionally, AI automates routine tasks and making the communication more efficient and also personalized. Finally, we come to the satellite internet constellation. These networks or artificial satellites aim to provide a global broadband internet coverage. They focus on connecting remote and underserved areas, ensuring no one is left behind in the digital age. Look at the positive impacts these advancements bring to the society. The first one is the high-speed internet access. With 5G, internet speeds can reach up to 20 GB per second, a significant improvement over 4G's typical speeds of 10 to 100 of megabytes. This translates to faster downloads, smoother streaming, and overall better user experience. It also brings a low-latency communication. The 5G reduces delays, which is essential for time-sensitive applications like online gaming, video conferencing, and telemedicine. Next will be the global accessibility. The AI and satellite internet constellations enable connectivity across the globe, making the information and ideals and cultures more accessible to the public. This fosters inclusivity and strengthens the global connections. And the last one will be the support for IoT applications, which is the Internet of Things. The satellite constellations also play a crucial role in the growth of the Internet of Things by connecting the devices. The applications like smart traffic management, surveillance, and emergency response systems improve the public safety and efficiency. While the communication technology has brought the incredible benefits, it has also been subject to some misconceptions. Now let's look at some of the misconceptions we have. The first one is the health concerns. There is a widespread belief that prolonged exposure to communication devices poses severe health risks. However, scientific studies have shown no conclusive evidence to support this claim. Our resolution is to raise public awareness about the research findings and also encourage responsible use of communication devices. The second one is the safety of the infrastructure. Another misconception is that communication infrastructure like towers is inherently unsafe. In reality, these structures are governed by rigorous safety standards to ensure the public safety. And our resolution is to emphasize the adherence to these protocols and engage with communities to address any concerns. We also have some misconceptions about privacy and also cultural sensitivity. Now, let's address concerns about privacy and cultural sensitivity. For the privacy and legal concerns, many believe that digital communication compromises privacy and intellectual property. However, the robust legal frameworks exist to protect individuals and businesses, and our resolution is to advocate for compliance with the legal standards and work standard towards the strengthening regulatory frameworks to ensure our data security. And for the cultural sensitivity, there's also a fear that communication technologies may disrespect cultural nuances. When deployed thoughtfully, these technologies can bridge cultural gaps rather than create them. And our resolution is to emphasize the cultural sensitivity in the design and implementation of technologies, fostering inclusivity and celebrating global diversity. That's all for our group presentation. And thank you for listening to our group, and see you again. Goodbye.